Hi there and welcome back to the College Physics series. Today's video will be an in-depth analysis of the most important forces in mechanics. So the forces that affect how objects move. We're going to be going through a short list of them and we're going to be understanding them in detail. Thank you for being here. Let's get started. Every force around us, whether it's the steady pull of the earth or the subtle tension in a stretched string, tells a story. A story of invisible threads that hold the universe together, keep planets in motion, and even let us feel the solid ground beneath our feet. Today we embark on a journey through a short catalog of forces. These are the forces that shape our daily lives, govern the motion of objects, and underlie the interactions between everything we see and even those we cannot. Our journey begins with gravity, the silent architect of order in the cosmos. Gravity is the long-range force that pulls a rock toward the Earth, binds the planets in orbits around the Sun, and gives structure to the universe at the largest scales. Here on Earth, we know gravity as weight. This is the gravitational pull the Earth exerts on objects near its surface. The weight of an object, symbolized as W, is more than a concept. It's a real, measurable force directed straight down toward the Earth. The two biggest concepts here are that weight is a force and that it always points downward. So here I have 5 scenarios where an object is thrown up in free fall, where it is dropped or can be thrown downward, projectile motion, an object rolling in 1D motion, and an object sitting at rest. What all of these scenarios have in common is that the weight of the object is always pointed downward. No matter how an object moves, its weight vector always points downward, connecting it to the vast mass of our planet. Remember, weight isn't the same as mass. Mass is the measure of how much matter an object contains, while weight is the pull exerted on that matter by Earth's gravity. Next, we encounter the force of a spring, a versatile force that can both push and pull, depending on whether the spring is compressed or stretched. So let's say here I have an object connected to a spring, and we're going to call this its equilibrium position. This is the normal. If I put my finger and I compress the spring towards the left, so that way it maybe looks a little something like this, I squish it. What the spring is going to do, it's going to exert a pushing force. So here's the equilibrium line. The spring wants to come back towards this line, so it's going to be pushing in this case. If I do the opposite thing and I grab the box from its equilibrium and I pull it so that the spring is now stretched farther compared to its equilibrium line, then the spring is going to exert a pulling force, or it's going to want to come backwards to this equilibrium line. And that is an example of how a spring can both push or pull. Springs are interesting objects because they always want to return to its natural shape. And this concept is what we call a restoring force. The spring force is labeled as FSP. So the capital F with the arrowhead indicates that this is a force, and the SP is just short for spring. The spring force arises from a unique tension within the object's structure. Whether in a metal coil or a bending piece of wood, each molecule is connected by what we call, or what we motto as, tiny springs that resist changes in shape. Through these microscopic bonds, springs become powerful examples of how elasticity enables structures to withstand and recover from forces applied to them. To reiterate the importance of the spring force, let's take an example of just a box that's made of wood. If we zoom in to the internal structure of a box, it is a solid, and we're going to see atoms tightly pressed together. It's very compact and very rigid. What we find is that solid objects are not perfectly rigid. There's some leeway for objects to be compressed or to be stretched. So when we think about the molecular structure of solids, we model the molecular bonds as springs connecting each atom together. This is why when you press down on an object, it seems to squish. You can compress it ever so slightly. Just like on a larger scale, when we have this sort of spring that can be pulled or pushed, you can do that at the molecular level. At least that's the way that we model it. This has not been directly observed. When we pull on a rope, a new force emerges, tension. Tension represented by capital T. We can call it capital T with an arrowhead for tension, or the force of tension, Ft. You can see it either one of those ways. Tension is the force exerted by strings, ropes, or wires when they pull on an object. A major idea is that tension is only able to pull on objects. And you can try this out. You can have a string or a rope connected to an object, and you can try pushing using a rope. You're going to find that you're going to be very unsuccessful with that. So you can never push with a rope. You can only pull. The direction of tension is always along the string or rope itself. In this picture at the right, there's a person pulling horizontally using a rope. So the tension is then directed horizontal. If the person were pulling at an angle like this, then the tension would be directed at an angle as well. Imagine looking at a rope under a microscope. You'd see molecules bound together by flexible atomic springs. So let's imagine. I'm going to analyze this middle section. We're going to blow it up. The molecular structure of a rope can be modeled like this. And like we mentioned before with springs, we can imagine atomic springs connecting each atom. So when you pull towards the right, creating the tension in that rope, you're also pulling on each of these atomic springs a little bit to the right. So the pull from your hands gets transmitted to each one. You pull on this atom, it's going to stretch this spring and it's going to pull on this next atom, which is then going to pull on this spring, which then pulls on the next atom, which then pulls on the next spring and the next atom, and so on. So you're going to continue the train until you get to the object itself. These molecular springs stretch when you pull on the rope, transmitting your force through every molecule until it reaches the object at the end. Tension is more than a single pull. It's a chain reaction of microscopic forces within the material, connecting you to the object on the other side. Consider the book resting on a table, or your hand leaning against a wall. The force that pushes back against you is called the normal force, symbolized as a lowercase n, or Fn. It's a reaction from a surface, always directed perpendicular, or normal to the surface. The word normal means perpendicular. So for this book, the normal force is always going to point perpendicular to the surface. So here I get a right angle. Here I have a person applying a force this way on the wall and touching the wall at this point. So the wall is going to push backwards, normal. And this will be my normal force, both of those two arrows. So the person leaning on the wall is pushing towards the right, and so the wall is going to push left. If you have an object that's on a ramp and I have a box sitting on it, perpendicular to the ramp is here, like this. You're going to create a 90-degree angle, and that is how the normal force behaves. The normal force is invisible, but it is essential. Without it, you'd fall through the chair you sit on, and your hand would sink through the wall. At the microscopic level, the surface is full of molecular springs, as we've been saying. These springs compress under the object's weight or your hand's pressure, pushing back in response and giving structure to the solidness that we take for granted. So if we were to zoom in on an object that sits on a surface, so wherever the book is coming into contact with the table, we can zoom in here as an example. So we're going to zoom in, and what we originally got before is that in solids, the molecular structure is rigid. The normal force comes from a deformation in these springs. So instead of being exactly straight, we model the molecular structure as being slightly warped under the weight of an object. So together, these springs are bent in such a way that the force that they transmit is upwards. And that's what we feel as a normal force. And of course, we can complete the structure as such. This is the reason why we believe we can feel objects. So your fingertips, the atoms along your fingertips touch upon the atoms of another object. And the interaction of these spring forces that we think about are what we perceive as why objects are solid. So this is not the definitive explanation. It is just a model that we use that can explain why objects are elastic and why we can feel things as being solid. If you've ever watched an object slide to a stop or tried to move something heavy, you've met friction, symbolized as F, or capital F for force, lowercase f as a subscript to read force of friction. Friction is a force that resists motion. There are two kinds of friction. We have kinetic friction and static friction. Kinetic friction opposes objects sliding across a surface. Static friction keeps objects stationary until you apply enough force to move them. The frictional force is always parallel to the surface. So you only experience static friction when objects are at rest, when they are not in motion. Once objects do get in motion, then you switch over to kinetic friction. Let's try a quick example. So this example reads, a book is resting on a slope. Given what you've learned about friction, what can you say about the friction force acting on the book? So we just learned that there are two types of friction. One for motion, one for objects that are not in motion. So because this book is resting on a slope, then only one of these types of friction applies. Here, I'm going to be experiencing static friction. If there were no friction, so if the surface were frictionless, the book would slide down the incline because gravity is always pulling down. The book would not slide up the incline because there would need to be some additional force to push it upwards. So if the direction of motion would be downward, what we know about friction is that it always resists motion. If it resists, then that means it always points opposite to the direction of motion. I know it's going to point opposite to the direction of motion, so it's just going to be completely the opposite way. And it is always parallel to the surface. And I find that this line for Fs is parallel to the incline itself. So here are two things that I can say. I can say that there is a static friction force directed up the slope. Microscopically, friction arises from the interaction of atoms between surfaces. Rougher surfaces increase friction as more atoms come into close contact, resisting motion with a greater force. Friction is a subtle yet powerful force, working silently to bring moving objects to rest. Next is the force that we call drag. Imagine holding your hand out of a moving car window. You feel the air pushing back against your hand. That is drag. We label drag as a capital D. Drag is a resistive force experienced by objects moving through fluids. Later in this series, we are going to define what fluids are. But for now, you can think of objects like air or water. Drag always points opposite the direction of motion, becoming stronger as the object moves faster. If you drop a piece of paper and a rock from the same height, drag explains why the piece of paper always loses, even though we know that gravity accelerates all objects at the same rate. The drag on a rock is much lesser than the drag on a piece of paper because of its surface area. So both objects are going to be moving down, but the drag affects the piece of paper more. And we would say that the drag points upward. And for the rock, the drag would be much smaller in comparison. From the gentle resistance on your hand to the powerful force felt by a speeding airplane, drag is a reminder that even invisible fluids shape our world. For a jet or rocket, motion requires thrust, a force created by expelling gas molecules at high speed. Thrust is simply labeled as F thrust. Thrust propels an object forward, opposite to the direction in which the gas is expelled. So if we think about a rocket, it is going to expel gas downward. And what happens oppositely is that expelled gas downward is going to help push the rocket upward to create this force of thrust. Although subtle, thrust is a transformative force. From rockets exploring space to airplanes crossing continents, it showcases humanity's ability to harness energy and achieve the once impossible. Finally, there are forces that operate across distances without any physical contact. Electric and magnetic forces. These are long-range forces that act on charged particles, fundamental to the technology around us, from the circuits in our phones to MRI machines in the hospitals. Although we'll dive deeper into these forces later in our series, they remind us of the invisible yet powerful interactions underlying modern physics. Each force we've encountered, from the weight of a falling rock to the tension in a rope, represents a thread in the intricate web of physical interactions that govern our world. They are the tools we use to describe motion, predict behavior, and understand the universe. Forces aren't just abstract concepts. They are the touch points between objects, connecting everything in a cosmic dance of cause and effect. And as we continue exploring, these forces will be our guides, revealing the hidden mechanics of the world around us. Here's a question for you before we wrap up. The Try It Yourself problem reads, a box is being pushed across a rough horizontal surface to the left. What are the directions of the applied force and kinetic friction force acting on the box, respectively? You have 4-letter choices of left, right, left, and right. If you found this video helpful, consider liking, subscribing, and sharing it with someone who might benefit from it. Thank you for being a part of the College Physics series. I look forward to seeing you in the next lesson.